Hello, today we're going to present a paper about EdgeSAM. If you have ever tried Galaxy's AI Eraser or cleanup feature on iPhone, you will know that you can select or remove objects just by a couple of touches. These are done by promptable segmentation, and the representative model is called SAM, which stands for Segment Anything Model. But SAM has some limitations. It requires large computation resources and high memory usage, which means it's unsuitable to run on smartphones. We can make the model smaller and faster to run on smartphones, but it results in huge performance drop. So we introduce EdgeSAM, a new model optimized for mobile devices. The architecture of EdgeSAM is based on SAM, and SAM is composed of three components: an image encoder, prompt encoder, and mask decoder. First of all, image encoder receives image and extracts key visual features. Using vision transformer, input images converts to feature map. Next, prompt encoder processes user's prompt. User's prompts are in form of point, box, mask, and text. EdgeSAM focuses especially on point and box prompts. Point prompt encodes location information based on clicked coordinate, and box prompt uses the corner coordinate of rectangular area. In this process, we use positional embedding and type indicator token to distinguish position and type. As a third component, mask decoder generates final mask by combining feature map from image encoder and output data from prompt encoder. Using the mask prediction token to generate masks and the IOU prediction token to evaluate their reliability, each pixel in the image is classified as either the user-specified object or background, and the mask with the highest reliability is selected. EdgeSAM is built on the SAM architecture we explained earlier. It keeps encoder-decoder structure of SAM, but differs in the image encoder. Instead of VIT, EdgeSAM uses CNN-based backbone like MobileNet v3 to reduce computations. EdgeSAM uses two key strategies to achieve similar performance even after replacing the heavy VIT-based image encoder with a lightweight CNN-based encoder. First is encoder-only knowledge distillation. Knowledge distillation is a training method to efficiently transfer knowledge from a teacher model to a student model. In this case, SAM takes on the role of teacher and EdgeSAM takes student. Second is prompt-in-the-loop distillation. We'll discuss more about these 2 points on the next page. The training process of EdgeSAM consists of 3 steps, each with different goals and strategies. The first step is encoder-only knowledge distillation. The primary goal is to train a lightweight CNN-based image encoder to extract image features at a level comparable to the original SAM model. If you take a closer look, a CNN-based RevVIT is selected as the student model because it is optimized for mobile environment and it is known for exceptional performance on edge AI accelerators such as iPhone's neural engine. In the training process, identical input images are provided to both the teacher model and the student model, and the resulting feature maps are compared pixel-wise to minimize the differences between the two feature maps. During the process, the training proceeds in the way of reducing the feature representation gap between teacher and student using mean-squared error as the loss function. Now let's say that the encoder is the only component that can produce feature maps similar to those of the teacher SAM through knowledge distillation. But the paper mentions that just training the encoder like this is too task agnostic, so it cannot really learn all the knowledge that SAM has. By saying task agnostic, it means the approach only tries to match visual representations without considering segmentation. This experiment was presented in the paper, but since we are running out of time, I will briefly mention it. To put it simply, training CNN-based student encoder with only 1% of SA1B means its representation ability is inevitably limited. Even if the CNN creates feature maps similar to the teachers, it is hard to perfectly match with the mask decoder. So, to improve segmentation performance, we need to fine-tune decoder too. To solve this problem, the paper proposes a method called prompt-in-the-loop distillation. In other words, it means training the mask decoder to fit the newly trained encoder better. So here we input the same point and box prompts into both the teacher SAM and student models to find the areas the student missed, which is called false negatives, and the areas it wrongly included, which is called false positives. If you look at number 1 in the image, you can see that unlike the SAM model, EdgeSAM missed the model bearer in the mask it generated. Number 2 shows how positive points are automatically created on the missed pixels. In 3, these positive points are then added to the original prompt and we retrain the student model to get a corrected mask. This loop of predicting, analyzing errors, updating prompts, and repredicting is the core of the prompt in the loop distillation strategy proposed in EdgeSAM. Here we use a combination of dice loss and BCE loss. Specifically, pixels that the teacher mask predicts with a probability of 50% or higher of being part of the mask are assigned a level of 1 to create a pseudo mask, which is then compared with the student mask to calculate the loss. As a result, we can train a student model that is robust enough using just 1% of SA1B. Here you can see comparison of performance between SAM and its variant models. FPS on the third column stands for frames per second and higher value means better performance. As you can see, EdgeSAM has higher FPS points than original SAM. MParam shows how many parameters the model needs to learn, basically how big the model is. If the number is small, the model is lightweight. Gflops tell us how much computation the model needs per second. Again, the lower the better. It means the model runs more efficiently. Compared to SAM, we can see that both MParam and Gflops are way smaller. Then let's take a look at the experiments under various conditions. Since web demonstration already exists, we developed our own application that runs on Android device. The main feature we implemented are shown on this slide. Here are the codes how we pre-processed the image and passed into image encoder. And this is how we encoded point prompts and passed it into mask decoder. Now, let me show you a demonstration of the application running on Galaxy Note 8.
When the application starts up and an image appears on the screen, the user can provide a point prompt by touching the screen. When all three prompts are given, the mask decoder is executed and the resulting mask is overlaid on the original image. The user can repeat this process to attempt segmentation for each object present in the image.
And this is another one running on iPhone 15 Pro. To wrap up, let me summarize the key factors that influenced EdgeSAM's performance and their effects. First is prompt in the loop knowledge distillation. It shows great performance even with ambiguous prompt like a single point. It is effective across all backbones and running one iteration proves to be the most efficient. The second key point is the CNN backbone. While most SAM variants use VIT-based backbones, EdgeSAM uses RevVIT, which is CNN-based. CNNs are well optimized on most AI accelerators and show great performance in both speed and accuracy. Finally, there's distilling strategy, the two-stage method which distills only the encoder first and then applies prompt in the loop, performed better than the joint method. Through various design experiments, EdgeSAM showed fast and accurate segmentation and its key strengths lie in the prompt in the loop method, the CNN architecture, and an efficient training strategy. Thank you for listening and feel free to ask any kind of questions.